So let us spend some time talking about how can we extend the fundamental Ohm's law to tackle any kind of circuits that we encounter in real life. Let us recap very quickly what Ohm's law was all about. So let me just quickly make sure that we have the right. So Ohm's law essentially states that the voltage across a closed circuit is equal to R multiplied by I. V is actually measured in volts, R in ohms, and I, which is the current, in amps. Now, we can actually extend this basic principle to a large variety of circuits. Take for example, we have a circuit which is in serial. So we have a resistor R1, we have another resistance R2, and we apply a voltage V across this simple circuit. When we apply, we have a current which is flowing in this direction, and basically what we land up is, this is voltage V, the voltage at this point is V1, and then the voltage at this point we assume will be the same as this, which is 0. If we apply the Ohm's law, what we get is V minus V1, which is the voltage across this circuit, this is the circuit that we are talking about, is equal to R1 I, and V1 minus 0 is equal to R2 I. And if we solve this equation, we essentially get V is equal to R1 plus R2 into I, which can be represented by R effective for serial circuits into I, which means that when we have two resistors in series, the effective resistance of that circuit becomes equal to the sum of the individual resistors. Two things that you must remember. The voltage at this point, V, falls to V1 at this point. This is the other point. So assuming this is A, this is B, and this is C. This is the voltage at A, this is the voltage at B, and then across the resistance it falls to C. So the voltage as we measure across will continue to fall, but the I, or the current, remains constant. When we look at the other type of circuit, which is known as putting resistors in series, we get a slightly different situation. Out here, the I actually gets divided amongst the two resistors into I1 and I2. The voltage across A and B, that means across each resistors, remains the same. So, as opposed to a situation here where the voltage was falling and the current remained the same, in this case the current is actually changing. It changes across the different ones, and the voltage essentially remains the same. So we apply that the I is equal to I1 plus I2. I can be written as V, or effective for parallel circuits, is equal to V upon R1 plus V upon R2. Then we come up with the other formula, which is V effective parallel is equal to 1 upon R1 plus 1 upon R2. So this is one formula, and the other formula that we see is here. So what we will now show you is how to use these two basic equations, which means when you have resistors in series, you will simply add them up. When you have resistors in parallel, what you have to do is 1 upon R effective is equal to 1 upon R1 plus 1 upon R2 plus 1 upon R3 plus 1 upon R4, as many resistors that you may have. Now let us see how we can extend this logic to slightly more complicated circuits. Equation, we have a circuit where the voltage is 220 volts and we want to find out what is the current which is going through this resistor and this resistor. This is obviously something in series, so we say resistance in series would be equal to R1 plus R2, which is 10 plus 12, which is equal to 22 ohms. So the current is going to be equal to 220, which is same as the voltage across, divided by the effective resistance, which is 22, and that gives you 10 amperes. So what we have to write here is 10 and we have to write here 10. But that's how you solve a simple problem. Let us see how we can take this to the next level of complexity. So this is a slightly more complicated problem. What you have is a resistor, another resistor. These are obviously in series. These two guys are in parallel. But what we will show you is we now will replace this complete circuit out here by one single effective resistor. And let us see how we do that. So the way to do that would be that we take the effective resistors out here would be equal to 1 upon Rp is equal to 1 upon 3 plus 1 upon 6, and you can do that calculation and it will show as 1 upon 2, which means Rp is equal to 2 ohms. Right? So now what happens when we define that this circuit can be replaced by a resistor of 2 ohms? Let us see what does the net impact of that calculation is. So this essentially becomes the net impact of the calculation. And what we now have is a simple scenario of 3 resistors in series, and we can now do the calculation. So the voltage is 220 volts, divided by 17 plus 3 plus 2, which is equal to 10 amps. And so what we can easily come out and put is 10 amps, and to this circuit it would be 10 amps. But we must remember that the circuit out here does not really exist. What we will have to now go back and replace it with the original 2 resistors that we started out with. Let us see how we do that. So now as we see, we have 10 amps and 10 amps. The current flowing into this circuit is again 10 amps. Now the 10 amps will now have to be broken up such that the voltage drop across this remains the same, which means 6 ohms multiplied by 10 has it has to be 6 multiplied by I1, which is the current which is going here. This is say I1 and this is say I2, is going to be equal to 3 into I2. Simply put, I1 upon I2 will be equal to 1 by 2. Implies if now I1 plus I2 is equal to 10 amperes. We can simply solve this equation using ratios and proportion and come up that I1 will be equal to 3.3 amps and I2 will be equal to 6.6 amps, which is what we would expect, because the one with the lower resistor should have the maximum current to ensure that the effective voltage drop is the same across the one with a higher resistor and a lower current. With that, I conclude this lesson.